Okay, so good morning, everyone. So there will be a lab submission next week. Okay, I just post the announcement. So the last lab submission will be next week for week 9. And if you look at the problem, it will be the Euler method. So it will be exactly the first part of your project. So very relevant. So if you started to do the project already, then the next week lab submission will be very straightforward. But if you haven't started, then the next lab submission is just like to make you to start working on the project. Because some people leave, the project for the last week. So last week we was talking about the Euler method. We started talking about Euler method. So I will show you how to implement this Euler method. Sorry. So remember last time, so this one is available in Moodle, okay, in the lecture notes for the last topic. So you see that, so this is a function that implement the Euler method. So you can enter, the input parameters can be a function f, yeah, f for the right hand side. So maybe let me make it a bit bigger. See, so it has a t0 is the initial time, t max is the end time, y0 is the initial data, and n is the number of subintervals. And this is just a summary. So first you divide the step size. Yes, the step size, uniform step size is just the final time minus initial time divided by number of subintervals. And then, you define the initial data. So initial data is just y0 here, okay? And then capital Y is two-dimensional matrix, okay? So why is that? Because, the initial data can be a vector, okay? And then, so first you initialize the first entries, yeah? And so this one is just a formula of the Euler method, okay? So this is the function that solves the ODE by Euler method, and you can assume that the initial, the y can be a vector, yeah. So initial could be a vector. So maybe we start with something similar than this. So maybe we start with something. Maybe just make it simple, right? So suppose last time, remember what we have is the function f. So if you remember the So maybe we start with something similar then. Yeah, so maybe we start with this one. So suppose I have y prime equal t plus y. Okay, so we solve y prime y prime or dy over dt, yeah, equal t plus y. Okay, and you know your initial condition is y0 equal 1. Okay, and now we know the exact solution is yt will be 2et minus 1 minus t. 2et minus 1 minus t, yeah? So now, let's see whether I can solve this by Euler method, okay? So now we have the function, okay? So maybe we define f first, yeah? So step 1. So we do it step by step, yeah? So step 1, we define the function f. So f will be, well, f is an anonymous function. So it will be like ty, okay? And it will be t plus y, okay? And now you have y0, so initially I just put y to be 0 because, you know, I just initialized, so n is the number of subintervals. So how many subintervals? Suppose we just put like 10 subintervals, yeah? So number of subintervals. Okay, so then you have, what is the step size? So step size will be, you know, suppose I want to solve what is t0 and what is t max. So I want t0 to be 0, yeah? So t0 to be 0. So this one is my initial time. And then my last time, so t max will be, say, 10, yeah? So in this case, then I want, you know, I mean, well, maybe the last t just equal 1, yeah? So then the step size will be t max minus t0 divided by n. So remember we subdivide the intervals into equal space, yeah? So that's why the width is just equal t max minus t0 divided by the number of subintervals. And then, and now what you want to do is you want to implement the formula. So now my y0, because I cannot start with 0 because the index in MATLAB start with 1. So I just set it equal 1, yeah, initial condition. So this one is my initial condition. y0 equal 1, yeah? And now I implement Euler method. So for k from 1 to n, so yn plus 1, or sorry, yk plus 1 is just equal yk. So this one is just the formula of Euler method. So if you remember, so this one is just the formula of so so what is t? So tk, so tk is just h times k, right? Because remember the width of the step size is h, and at k equal 1, then it just so let's see. So now when t equals 0, no, I mean this one k should run from, yeah, k run from 1 to n is correct, yeah. So t1 is 0.1 times 1, okay, so it's correct. So t2 is 0.2 times, so it's correct, yeah. Only we have to shift k because, sorry, we have to shift y k plus 1 because the vector y cannot start from 0. Okay, and now, but then it means that this one has to be n plus 1, yeah. Okay, because you know the last step can be n plus 1. Okay, so now we run it. So you will see that now if I check the value of y, so what do I have? So where's my so errors in should be zeros like this, yeah. So you will see that, okay, so my y1 is 1, okay, and y2 is, so exactly here, so 1, sorry, get rid of this one. So you see, so at t equal 1, sorry, at k equal 1, yeah, then y1, you know, is actually y2 in our case, so 1.1, yeah, and then y3 is, I think it's a bit off, okay, so let me check. So no, actually according to this, then k has to run from 0, yeah. So k run from 0 to, so according to this table, yeah, so k has to run from 0 because you put yk here, then n minus 1 here, okay. So let me adjust this a bit. And here you have, okay, so run it again. YK. Well, if this one has to be, so then because this one should be k plus 1. Because if k equals 0, you have to assess the index problem. So this one should be k plus 2. Okay? This one's still plus 1. Okay, so let's see whether we have this problem anymore. So I want to implement exactly this calculation, yeah? Okay, so now check it again. So y1 is 1, yeah? So it's here. Y1 is y0 because, you know, we start with the index 1 in MATLAB. We cannot start with index 0. So then y2 is 1.1, yeah? So what is this one? Okay? And then y3 is 1.22, Yeah, so it's okay, yeah? And then y3, y4, yeah? So y4 is this one, okay? So essentially, you see that I solved this problem, yeah? So, I mean, by Euler method. And now I can plot it. So now I can plot my solution. So plot, so now my t will run from, t0 to t max, yeah? And then you have y, the vector y. Okay, so this one is your numerical solution. You just connect the dot. Okay, so you see that. So how about the exact solution? Well, because we haven't checked the exact solution, but you can check. Suppose I put in the exact solution here. So exact will be t2 times exponential p minus 1 minus t, yeah? So then I can plot again. So maybe let me put a plot command inside this, yeah? So where do I plot it? Plot this one, yeah? And I plot exact as well. So t0 maybe t max exact, yeah. And we plot exact like a red color. So you will see, no. Invalid second. No, sorry, it has to be. So I think I have to define exact u to be something. Exact is the function, yeah. So exact, this one is exact, yeah. So but actually we have to define it first. So exact u is exact applied to this vector. So maybe we just put the plot equal this range, yeah? And we just use it again and again. See, because we define exact to be the function, so we have to evaluate the data first before we plot it. Sorry about the confusion, but anyway, so now what you have is, you see, so your blue curve is the Euler method solution. The red curve is the exact solution. Okay, and you see, I mean, you can increase the number of subintervals. If you increase the number of subintervals, then you see that the two curves are very close to each other. Yeah, so that is the idea. And so in the project, if you look at the project carefully, what you have to do is the Euler method, not for one ODE, but 3 ODEs. 3 ODEs at the same time. So what you have to modify is, now your yk plus 2, okay? In this case, it's just a scalar. But in the project, it should be a vector. It should be a 3 by 1 vectors. Okay, so you need to modify only this line. And then you have to put it in a function format. I mean, this one I just put in a script. Yeah? But then if you put in a function format, then it's just a few extra steps. But that's the idea. Okay? Question? Yeah, this one. Doesn't matter because, I mean, when you allocate this, it means that you just allocate the memory in advance. So if you don't do it, then sometimes MATLAB will slow down a lot. You just allocate. Okay, so in this case, you just allocate the, n+1 empty space and set it equal 0. But after that you modify, because it is the first entries become 1, and all other entries got modified by this Euler formula. Okay? Yeah, so that is about the Euler method. And now we discuss about the errors. So like last time I showed you this pictures, yeah? So you can so you can compute the errors. So suppose we have the exact solution, you can compute the errors, yeah? And the errors, you can take the errors, maximal errors over on the subintervals. Yeah, so in this case, so this one is a different ODE, and you put in when h equals 0.5, you got these errors. Yeah, and if you reduce h is 0.2, you got these errors. So again, so this one, if you look at the project description, what I want you to do is just this max errors. Okay, so the errors not at every time step, but you take the maximal of every step size. Okay, so this is the errors. Otherwise, there's a lot of numbers, right? So what you want is what I want is just take the maximal of those numbers in absolute value. Okay, and give you this. And now, if you decrease h is 0.05, then the errors reduce. So roughly, what is the order of conversion? So can you guess? Suppose h equals 0.2, then I decrease h by 1/2, then the errors roughly decrease by 1/2. So what is the order of conversion? 1, yeah? So, and now we are going to prove it vigorously. Okay, so now, let me try to prove it. This is a theorem. So first, we define local truncation errors. So what is a local truncation errors? So local truncation errors is defined to be this quantity. But what does this mean? So what does this quantity measure? So what does this quantity measure, in our ODE? So WISE has a name local truncation errors. So now look at this one. So when h goes to 0, what is the first term go to? Derivative, right? Because if you remember, this is exactly your definition of derivative. If you take limit when h goes to 0, this one is just y prime. Yeah? So then t, the local truncation errors. Okay, so first we just say that in the limit, this one will go to y prime, yeah, as h go to 0. And so this one is still f t y t. So what is our ODE? So our ODE is just y prime equal f at ty, yeah? Remember? So therefore, this one will go to 0. So therefore, t will go to 0 as h go to 0. So more or less the local truncation errors, it just measure, like how good your numerical approximation to the exact solution at the time t. Okay, so we fix the time t, yeah, and we let the step size h go to 0. Then the local truncation errors should go to 0. Okay, so that is the reason, because this guy go to 0. I mean, when you fix t, yeah, and then it will go to y prime, and y prime minus f is exactly our ODE. We want to solve it. So this one has to go to 0, right? So because y prime equal f. Okay, so now once I define this, so now go back to the errors. So the errors, it just, this one is my exact solution minus my numerical solution, yeah, at the time tn. Okay, so now I just put t equal tn. Okay, so if I put t equal tn, then what do I have? So t equal tn, so put t equal tn, then I have y tn plus h minus y tn. So because we're just interested in the local truncation errors as the point we are doing the numerical calculation, right? Other point is not applicable. And so this one will be tn y tn. Okay? And now because tn plus h, so remember tn plus h is just equal to tn plus 1. Yeah, because we divided uniformly, yeah? So therefore, you can have this one is just tn is y tn plus 1 minus y tn. And now I multiply by h, so I got h here minus h f tn y tn. Okay? And I rearrange it a bit more, so I just, move everything here to one side and move this one to another one, yeah? Then I have exactly this equation 10. Okay? So then I just have y tn plus 1 is just y tn plus hf tn y tn plus h tn. Okay, so that is exactly what I have in this equation 10. So put a box around this, and then we compare with number 7. So what is number 7? So 7 is, so it's a definition of the Euler method. Yeah. So here you have yn plus 1. So the Euler method, you have yn plus 1 is yn plus h f tn yn. Yeah. So then when you minus the two of them, then you have y tn plus 1. Huh? So you minus two of them, you have y tn plus 1 minus y n plus 1 equal y tn minus yn plus h f tn y tn. So this one f tn yn plus h tn. Okay, so that is the the new relation. So and I think this one is in the slide, if I remember correctly. Okay, so so we just have this new relation, yeah. So now what you look at this equation, okay. So on the left, it will be your errors. So remember the errors is just ytn minus yn. So this is the error at time n plus 1. And this is the error at time n. And you have to do something here. You have to do something here, right? So this one is nothing but en plus 1, yeah? And this one is nothing but en. Okay, so now you have some relation between en plus 1 and en. And for this term, we have to use the Lipschitz condition. Okay, so if you remember Lipschitz condition, so Lipschitz condition is this assumption. Okay, so there's a constant, so that the difference between f t yn and f t y2 is just bounded by L y1 minus y2. Okay, you have to use that assumption in order to have this one. So this one will be bounded by the whole thing here, yeah. So will be bounded by So maybe let me rewrite it. Okay, so this one will be en plus 1 equal en, okay, plus h f tn y tn minus f tn yn plus h tn. Yeah, and I will use a Lipschitz condition in order to bound this. So this one will be L time. So en plus 1. So if I take an absolute value, yeah. So en plus 1. Let's see whether I have it in the slide or not. So but just write down first, yeah. So en plus 1 will be less or equal en plus h L y tn minus yn. Okay, and this one is nothing but en again. And because en is positive, so we don't know whether it's positive or not. So just put absolute value. But the n is, I think, could be negative. So put absolute value. Yeah. So this one I combine the two terms, so it will be 1HL En, yeah, plus HTN. Okay, so I have something like this. So I have the errors at step n plus 1 somehow related to the errors in the step n by this relation. Okay? And we have to use the Lipschitz condition for the function f. I might have it in the slide, so let me check here. Yeah, so maybe I have it here, yeah. Question? Yeah. Still less than or equal to. Yeah, sorry. So should be still less than or equal to, yeah. Because you have to apply triangle inequality, yeah, because they could be negative, so you have to make absolute value. Yeah, so essentially it's here. So I summarize here. Yeah, so essentially you got to this line, yeah. So En plus 1 absolute value less than 1 plus HL En and plus H epsilon. So what is epsilon? So now epsilon will be my maximal local truncation errors. Yeah, because this Tn is at time T1, T2 up to Tn, T capital N. Yeah. So I just take the maximal. So this epsilon is nothing to do with the machine by epsilon. Okay. So this is a notation only in this proof. Yeah. So if you take epsilon to be the max of all the local truncation errors, then you have this relationship. Okay. But now before we move on, now go back to what is Tn. So can we estimate Tn before we move on? So Tn is local truncation errors. Okay? And Tn actually is of order h squared. Okay, so that is the proof here. So the proof here is the local truncation errors is just order, not h squared, sorry, order h, because this one h, and then this one is something of higher order. So now how do we arrive at this calculation? Okay, so we just stop here because we want to estimate Tn separately, yeah. So Tn is the local truncation error. So we will resume this after we estimate Tn. Okay. So now suppose we have T capital T will be the local truncation errors will be Yt plus H minus Yt over H minus F Tyt. Yeah. And you can use Taylor expansion. So if you have Taylor expansion of y of the function y around t, then Yt plus H is just equal Yt, plus Y prime T H plus Y double prime T H square divided by 2 plus some higher order. We don't have to worry. Okay. So therefore Yt plus H minus Yt divided by H is just equal Y prime T plus Y double prime T H over 2 plus OH square. Right? And then you plug it in here. So plug it in here, then you have T capital T will be Y prime plus Y double prime T H over 2 plus OH square minus F Ty. Yeah, but because Y prime and FTY are the same, yeah, so because it's an ODE. So that's why you have only y double prime t h over 2 plus os square. So exactly this one. Yeah. So in this case, then, you know, your Tn is just order h. Yeah, so your Tn, so therefore Tn, which is just the local truncation errors at time capital N, is just of order OH. So remember, because we have the h here and h square here, so it's order OH. Okay, so this is identical to the slide. Yeah? So now, okay, I think now we can use the slide. Yeah, so the slide say that assume the function is Lipschitz, then you know you can get out the errors at the step n is bounded by this quantity. And if you look at this quantity, this will be a constant because L is a constant, Tn, you know, I mean, you just take maximo here, so this one is a constant, so it depends only on this term. Okay, so this term will be order OH. So that is exactly what we've been doing here. So we arrive up to here. Okay, so we just arrive up to En plus 1. Yeah, so we arrive up to here. So En plus 1 is the errors at step n plus 1 is controlled by this. Okay? And this Tn is controlled by this proof. So it's OH. And then now what you need to do is you just need to somehow make a telescope argument. So this can be carried from step n plus 1 back to step n. Then you go back to step n minus 1, step n minus 2, and so on. Yeah? So what you have is something like this. So E1 will less than E0, yeah, plus some term. So remember Tn is order h, right? So we have this, yeah. So this one is HTN, yeah. So then E2, you know, is controlled by E1 plus H epsilon. And then E3 controlled by E2 and so on. Yeah? So in the end, then you just have a telescope series. I mean, sorry, not telescope series, a geometric series. Okay? And you just sum it up by the formula. I'll give you like this. And this one in the limit, you know, can be approximated by exponential function. Yeah? And this is bounded by e to the LTN. So this inequality you can use mean value theorem to show it. So it's not hard. And so that's why, you know, this term is bounded by e to the L to the Tn. So Tn is whatever step you stop at. So now go back to the, and everything here is written in lecture notes, okay? You just know exactly what is going on because it's written in lecture notes. So now we just look at the final results. So the final results look like this. So the errors at step n, okay, is bounded by this quantity, right? Times the maximal of local truncation errors of every step. And you see this one, you know, I mean, if you fix L, remember L is a constant. Where does L come from? So L comes from the Lipschitz constant. Remember? So L comes from the Lipschitz constant, not the function f. We used it before. So Tn is your last time. So it's fixed as well. So T max, like T max. So therefore this one is fixed. Right? When you increase the number of I mean, when you decrease the step size, this one's still fixed, yeah? If you fix n. But this one is changing, so this one depends on the size of the step size, yeah? Because the local transgression errors here is just OH, H, depends on is a step size. So in the end, the errors of Euler method is just OH, yeah? Because this is a constant, right? And this one is H, so that's exactly what we prove, right? So any question about this one? So this one is just a proof, yeah? So in the end, then what you have for Euler method, you just have it order OH. So in the project, I don't ask you to prove anything. I just ask you to carry out the numerical implementation, and you compute the errors table, and from the errors table, you deduce what is the order of conversion. Okay? And for Euler method, theoretically, we should know that the order of conversion is just 1, OH. You know? But your numerical solution, I mean, numerical order of conversion could be different from 1, but should be close to 1. Okay? Should be like 0.99 or something. Otherwise, something wrong with your numerical implementation. Yeah? So that is about the Euler method. So should we take a break or move on? Or? So how do you want to do it? Take 5 minutes break? Or, yeah? So we start again at 11 o'clock, yeah? Okay, thank you. Yeah.
Do you have solution to the past paper?
Past paper, you mean past exam paper? I think we will discuss about past exam, you know, maybe next week. No, not next week. Should be week 11, because next week we have Easter.
Do you have solution to the...
I have the solution only to the previous exam. We will discuss it. Yeah?
What about,
for the year before.
what about 2017?
Huh?
What about 2017?
2017. I might not have it, but we can discuss about that. Okay? Yeah? F prime because the ODE. Because the ODE Y prime equal F. That's what we are trying to solve, right? So Y prime equal F, so that's Y prime cancel. Yes. That's what we are looking for. Yeah. Yes, next week. Yes. Okay. Yeah. Okay, so we start again, yeah. So you see that in the end, we have the Euler method. It's just order OH, okay, and so there's a constant e to the L Tn here, so it can grow, right, when Tn increase, yeah. So it means that when you use Euler method, you put in T max is 100. Then you got the errors bigger, then you put T max equal 1. Okay? So so that's why the longer you carry out the Euler method, the bigger the errors will be. So you don't want that. Yeah? So now we are talking about implicit Euler method. So what is implicit Euler method? So if you remember, we did how do we define Euler method? So we define Euler method like this. So y prime, or maybe, so we have y prime equal f of ty, right? And then we have y1 equal y0 plus integral f prime at t0 to t1, right? And so, this is an integral. So if we approximate by, so this one is t0, this one is t1. So if we approximate by a right-hand side rectangular rules, then you get this one to be y0 times h times f prime t0 y0, right? And then you have Euler method, right? The explicit Euler method. But now, so this one explicit. But now if I approximate this integral by something different, so y1 is y0 plus t0 t1 here, f prime dy dt. So instead of approximate the integral like this, I approximate by the right hand side rectangle, right? So if I approximate by this one, by this rectangle, so this one is a function f, yeah, this one function f, but approximate by this rectangle, then I will have y1 is y0 plus f at t1 y1, yeah? And then this one will be implicit Euler method. Okay, so that is the formula here. So if we approximate by the right hand side rectangles, then you have an implicit Euler method. And you see, y is implicit because you have y1 on the left and y1 on the right. Yeah, so it means that you have to solve an equation, right? Otherwise, this is not, so it's like implicit function. Implicit function, you define the function by, an equation. So here, y1 is defined implicitly by this equation. Yeah, it appears on the left and on the right. Yeah, and you see, if you carry on y2, y3, then eventually you got this general formula for yn plus 1. So here you have yn plus 1 on the left and yn plus 1 on the right. So implicit method. So every step, in order to get yn plus 1, you have to solve an equation. It could be nonlinear equation. It depends on f. If f is nonlinear, you have to solve a nonlinear equation. But you know how to do it, right? Yeah? We studied fixed point iteration, Newton method, second method. So you can solve it easily. Yeah? Okay? So that is the implicit Euler method. And now, what happens if I replace, okay, so yn plus 1 is implicit, yeah? What happens if I replace, this by a trapezoidal rules? So if I replace this by a trapezoidal rules, then I have y1 equal y0 plus t0 t1 f prime ty. So now I will replace it by 1/2 f t0 y0 f t1 y1. Yeah. So it will be like this. Okay. And you see that. So that will have a name, so trapezoidal method. Yeah, because that is the rules that we use to approximate the integrals. And that exactly this formula. So we call it trapezoidal method because of this relation. Yeah. So y1 is just y0 plus h over 2 f t0 y0 f t1 y1. And you can do it iteratively, then you got this formula for yn plus 1. Okay? So now the Euler method and the trapezoidal method, which one is more accurate in your opinion? Huh? Trapezoidal, right? Why? It looks better. But, huh? More subintervals? No, the same number of subintervals. Yeah. You just replace, before, see, you have only this term, then you have a explicit Euler, sorry, if you have only this term, yeah, then you have explicit Euler method. And if you have only this term, then you have implicit Euler method. Yeah, but you have the average of the two, then you have a trapezoidal method. Okay, but see, the problem with this method is you have to solve an equation, right? Every step. Remember, if you try to implement it, you cannot implement yn plus 1 equal on the left and yn plus 1 on the right. Yeah. Then you have to solve some nonlinear equation at every step. Okay. And now, so now there's a way to solve this. Okay, so by, say, fixed point iteration. So suppose you have, remember, so what we want is, so what we want to solve is y1, just forget about yn, yeah, just y1, yeah, equal y0 plus h over 2 f t0 y0 plus f t1 y1. Yeah? Okay? So that is what we want. We want to find out what is y1. So because y0 is given. Y0 is given as a initial data. Right? We always have it. So now how do I find y1? So now suppose I want to use fixed point iteration. So I will label this one to be u. Yeah? So label this one to be u. Then, you know, my fixed point iteration is just u equal gu. So this one is like g of u. Yeah? So you can solve this. Right? Then you solve it for y1. Yeah? Okay, so this one is a fixed point iteration. And now, so G will be your home thing here. So this one is your GU. So this one is defined to be GU. So if you replace y1 by u, then this is your right hand side. Yeah? And then, you know, so the equation here will be just y1 equal gy1. I mean this equation. Okay, so that's what it say here. So y1 is just gy1. Yeah. So if you put g to be the home thing here, so the home thing here gu. Yeah, with y1 equal u. Yeah. And now you can solve it by fixed point iteration, but you don't want to use many iterations. You want to use only one. Okay, so if you use only one iteration, okay, so this one is, we just remember that fixed point iteration, you have to assume that g has derivative less than 1, so just assume that it's convergent, yeah? Then what you have is a Heun's method. So if you use iteration, if you use fixed point iteration, okay? So fixed point iteration, so look at this one. So now this is my y1. So y1 is defined to be g of u0. Yeah? So, and u0 is the one given by the explicit Euler method. Okay? So remember before, what is your g? So your g is this, your g, so your gu is just y0 plus h over 2 f t0 y0 plus f t1 u, right? And now you just put u to be u0. So let u0 to be, you know, your solution come from the explicit Euler method. And you plug it in here. So you plug it in here. So gu0 is, you plug it in here. So you have y0 plus h over 2 f t0 y0 plus f t1. And now you replace, you know, u by u0, yeah? So you replace this by y0 plus h f t0 y0. So that's how I get this equation. I just rewrite it. I mean, I just rewrite this one. So how do we get this one? Yeah. So, but now, if you look at this, this equation, so what's so special about this one? So this one is no longer implicit, but it's explicit. Because on the right, everything is y0, t0. Okay? On the left, you have y1. So it's become an explicit method again. Okay? So this method was a combination of implicit, trapezoidal method with a fixed point iteration. But you use only one iteration in the fixed point step. Okay, so that idea was proposed by this main Heun's method, and now we have this method. Okay, and you can see that just by this formula, then you will improve the order of convergence. So let me try to run it. So if you use, the same example, you run it, you see that for for Heun's method, the errors, so this is the Euler method, yeah? So the Heun's method, so decrease by, so this one is, so you decrease H five times, yeah? So the errors here decrease about 5 times for Euler method. But for Heun's method, from 0.09 decrease to 0.023. So what is the order of the Heun's method? Roughly. Roughly. Not exact, but roughly, numerically. Can you do it like in your head? So here, H reduced 5 times. Okay, then you got the errors from here, go down to here, or maybe from here to here. So H reduced twice, yeah? So this one H 0.2, this one 0.1. So here 0.01, and this one is 0.0023. So how far does it go? Just make a guess. So order, yeah, so order S square, right? Yeah, okay, so try. But you can see it from the numerical results, right? So this one like 100 go down to 25, yeah? So roughly decreased by 4, yeah? And H reduced only by 2, and errors reduced by 4, so it should be order OS square, yeah? Just by look at the number, okay? So that's why Heun's method, you just have a simple extra step, but let's improve your conversion. Okay? And so, if you go further, you see that the errors of Heun's method reduce faster. So now the ideas of Ronstadt method, is more or less carry on the Heun's method to a further degree. Because Heun's method, it's just only up to order 2. But Ronstadt method, Ronstadt contribution is you can, up to any order. Okay, so that is the special contribution of Ronstadt method. And so now, let's discuss about the Heun's method again. Okay, so look at the ideas behind Heun's method. Yeah. So now, suppose you define Xi1 and Xi2 like this. Okay. Then, so now if you look at this equation again, yeah. So this one is y1 equal y0 plus h over 2 f t0 y0 plus f t1 y0 plus h f t0 y0. But you see that this one is complicated because it has f here, then inside has f again, right? So now let me make it a bit similar to read. So now I just label this one to be Xi1. Okay, so no, sorry, this one is Xi1, yeah. So this one is Xi1, and this one is Xi2. Okay, yeah. Then what I have is Xi1 will be y0. Okay. Then Xi2 will be y0 plus h. Here it could be any coefficient, right? So suppose we just put in some coefficient. Here it's just going to be 1, yeah? but it could be anything. Okay, then f t0 and well, this one should be t1, yeah. So t1 then this one t1, yeah. So t1. So t1, instead of writing t1, I write t0 plus h. Okay. And this one is so what we have here? No, still t0, yeah. No, t0 xi1, yeah, still t0. T0, but then y0 just xi1, yeah. Move up, okay, sorry. Yeah. So this one is still t0. So then y1 will be y0 plus h over 2. Okay, but h over 2, it could be any number, yeah. So it could be any number. So b1 f t0 xi1 plus b2 f, t0 plus h xi2. Okay, so that is, so you see, you can rewrite this formula in this form. Okay, so why I do this? Because my claim is that, you can have other methods, yeah, and it still gives you order conversion too, which is of this form. So the Heun's method is not the unique way to give you the order 2 conversion. Okay, so that's why we need this. So now, so suppose, you can write down a formula for A21, B1 and B2. Yeah? That make the order conversion is OS squared. Then you can come up with a new method. Okay? So that is the idea of Brunson and Cutter. So now we start with this, yeah? So in general, we start with a method like this, and you try to find out what are the magic coefficient B1 and B2. C1 and here it just have C2, yeah? So that you have the order conversion is OS squared. Yeah? And now in order to do that, we have to go back to the local truncation errors. Okay, so remember the local truncation error is very important when you try to estimate the order conversion of a method. Yeah? And here, so order conversion, the local truncation errors in this will be defined by this, of this method. So here, we don't know those coefficients, okay? So those coefficients will be determined, right? But now, we look at the local truncation errors. So here, you have, the limit of this one will go to y prime, okay? Yeah? But what is the limit of this one? So what is the right hand side here? Sorry, what is another right hand side? But what is those terms? Where does it come from? So look at 18. Yeah? So if you look at number 18, if I rearrange it, yeah, then I have, so number 18, yeah. So if I rearrange it, I will have yn plus 1 divided by yn over h equal b1f tn xi1 plus B2F Tn plus C2H xi 2, right? Okay? Yeah? So you see it? So now if I put in, so if I put in T equal Tn, okay, in the local truncation errors. So in this local truncation errors, so I put in Tn here. Then what do I have? So I have y Tn plus h minus y Tn over h, yeah, minus B1F Tn y, well, Tn and should be y Tn, yeah, be y Tn, yeah, then plus B2, yeah, so F Tn plus C2H, and this one is nothing but xi 2, yeah, so this one nothing but xi 2. Well, actually, this one nothing but xi 1 anyway. So because xi 1 is of yn. So yeah. So then you see that this one is nothing but yn plus 1 minus yn over h. So this one is y at Tn plus 1, yeah, minus y Tn over h. Right? So you see that the local truncation errors, you know, you measure, so this one is like the exact derivative when h goes to 0, right? This one exact derivative. And this one is your numerical derivatives. Okay, so this one is like, you know, because yn plus 1 minus yn is your numerical solution of the method, of the ODE. Yeah, so this one is your numerical derivative. You know, at h go to 0. And this is exact derivative, exact y prime at h go to 0. You see? So you see this local errors, local truncation errors, will determine what is the order of conversion of your method. Okay? And now, so you see, and so this one come from this number 18, come from your method. Yeah, so this one estimate what is the numerical derivative of your method, and this is the exact derivative. Okay? And now we try to analyze this one. Yeah? And make it order OH square. Okay? So that's the plane. So now you use Taylor theorem again. So suppose I use Taylor theorem. So this one you saw it before, right? So y, if you use Taylor theorem around the point T, okay, then you can get this one. But now there's one more step here. So now what is my y prime? So remember we are solving ODE, yeah? So y prime equal f, so that's why y prime equal f here. Okay? But what is y double prime? Well, y double prime is, I mean, if you remember the chain rules, yeah? So the chain rule say that, so you have y prime equal f dy, yeah? Okay? So then y double prime is you have to take this partial with respect to t of f dy, yeah? Because it's a chain rule, so you have to do two steps. First, you take partial with respect to f, with respect to t. Then after that, you take partial f with respect to y, and then partial y with respect to t, right? This is the chain rule. Sorry. Yeah, but this one is your y prime. Yeah, and y prime equal f. Okay, so therefore, you can write again as f, partial f with respect to y. Okay, so that is how I got this term. Okay, and the higher order term, I just leave it here. So I'm not going to change anything here. And you got OS3. Yeah? And now, so this is your method. Yeah, so remember the method here. So this one I'm going to use the Taylor expansion again. But this is the Taylor expansion of two variables. Okay, so if you remember Taylor expansion of two variables, you have to take partial with the first variable, what is partial with respect to time, and multiply with this increments. Okay, and then take partial with respect to the second variable, and then increments. Okay, and then some higher order term. Okay, and now you combine. So you combine two of them. So now let me combine two of them. Yeah. So in the formula. So suppose I put in. So this one I cut some step, but now let me combine two of them for you. Yeah. So now suppose I have t as before. Yeah. So is y t plus h minus y t divided by h minus b1 f of t dy, yeah, plus b2 f of t plus c2h, and the next term will be y plus h a21 f dy, right? So this is the original local rotation errors, and now we use this. Okay, so we use this, and then what we have will be, so this one will become f dy plus h over 2 partial f with respect to t partial f with respect to y times f plus y triple prime over 3 factorial h squared plus oh cubed. Okay, and then so we have to minus b1 f dy, yeah, then minus, so this one is just here, yeah, so b2, and I remember I replaced this one by the Taylor expansion here. I replace this one, so I have to have b2, and this one will be my f dy plus partial f with respect to t c2h plus partial f with respect to y a21h f dy, yeah, plus os squared. So see, I just combine it. If I combine it, then what is the common term? So common term for f dy, so will be f dy, and you have 1 here, you have minus b1 minus b2 here, so you have 1 minus b1 minus b2. Okay, so that is how I got this one. Yeah, and for the partial respect to t, so for partial respect to t, So partial f with respect to t. Then what I have is, so this one I have h over 2, yeah. Then I have, so this partial with respect to t, so b2 c2h, yeah. So b2 c2h, yeah. So b2 c2h here. So I got this one, yeah. So that's why I got the second term here, and then what is partial f with respect to y? So what is partial f with respect to yf? So partial f with respect to y times f. Then I have, so this one I have h over 2, yeah. So I have h over 2 here from this one, yeah. And then I have this term, yeah. So I have this one. So I have minus b2 a21h. Yeah, so that's why I have this one. And you see, so now what remain? I just put it in here, so I don't have to worry about the remain. Huh? Well, I just rewrite this. How I arrive this one? But it's just identical to this one, yeah. So just put one extra step because I don't put in the slide, but just an extra step when you get from the expansion of y and expansion of f to this one. So now you look at the last line, the last two lines. So now remember, what do you want? So after this calculation, you know, what do we want? So what do we want? Why do we do this calculation? Huh? Order equal? Yeah, order equal 2, yeah? Which means what? Which means, in this case, what do you want? Huh? So what you want is you have this one go to 0, this one go to 0, this one go to 0. Yeah? Then everything just order s squared. Yeah? Because see, I mean this one is a constant, right? This one order h, this one order h. You don't want that. You want that to be 0. And remember, you have a lot of choice for the constant. Okay? So now if I put 1 minus b1 minus b2 equals 0, and I got 1/2 minus b2 c2 equals 0, and I got 1/2 minus b2 a21 equals 0. Then the local truncation is just equal to s squared. Then I have an order 2 conversion, right? So what are those possibilities? See, so yeah, so those are the yeah. So I just rewrite in this form, yeah. But you can see that you know, I mean now you have a lot of choice because how many equations you have? So how many equations you have? 3 equations, yeah. But how many unknowns? How many unknowns? 4 unknowns. So this means that you have more freedoms than just one unique solution. Okay, and you can verify that Heun's method is just one solution of this. Okay, so if you put in, you know, those values, you know, b1 equal b2 equal 1/2, you got this 1, yeah, and but you know, Ron's got the method. can be defined by other coefficients, and it still satisfy order OS square. Okay, and you see, you plug it in here, so you still have 0 plus 1 equal 1, and you know, A to 1 time B2 still give you 1/2. Yeah, so you have 3 possibilities. So Heun discover only one possibility. Yeah, but Ronskatter, you know, by this analysis, he can find out all other possibility that give you order convergence OS square, just by analyze the Taylor expansion. Okay, and we are not going to derive the full, you know, explicit Ronskatter method of order 4, but the idea is there. You know, you just have to analyze Taylor expansion, you know, and then you make the lower order equal 0. So Ronskatter method define so now you can define Y1 is a linear combination of new terms, okay, of those combination, yeah. And you know, because those values are not known, so we approximate it by psi j. And then those psi j are given by those formulas. Okay? So those numbers are different for different Ronskatter method of different orders. Yeah, because you see, I mean, if you have order 2, then you have only 2 equations. Yeah, and those coefficients are given, you know, like before. But if you have order 4, then you have a different coefficients. And then after that, you know, you can define yn plus 1 based on this. Okay, so that is the idea how we derive Ronskatter method of order new in general. Yeah, but we just focus only on a few terms. Yeah, sorry, a few order. So you see, now the method will be completely defined if you know those coefficients. Yeah. So now look at this number again. You know, so it look like those numbers look like a matrix. The A to 1, yeah, look like a coefficient of a matrix. So that's why this one is like A to 1 stand for row 2, yeah, column 1, and this one is row 3, column 1, and row 3, column 2, and so on. So that's why you have this index, yeah. So the new I, so new stand for the row, and the I is the index after that. So it's like a column, yeah. And then, so A is a matrix, and B is just a vector that determines the combination, okay, of the F xi I. So how about C? So C just determine, you know, how far you shift from the end. It's a vector as well. So what you want to know is just 3 elements, yeah. I mean, the coefficient C, the coefficient B, and the matrix A, and it determine a Ronskatter method, and we call it a tableau, yeah. So arcade tableau, and you know, I mean, the order is just like a cab, you know, taxi, you know, CAB, yeah. So it's a taxi, yeah. Cab, yeah. That is how you know, you have the order of the coefficient of the Ronskatter method. So you see, now suppose we go back to the second order Ronskatter method. Okay, suppose you have a table like this. So how do I read it off from the table? So suppose I have a table, say, so this one is 0, this one is 1/2, this one is 1/2, this one is 0, this one is 1. Yeah? Then this one will be my C, so it will be my C1, yeah? Okay? and this one will be my C2, and this is my B1, and this one is B2, yeah? And then, so what is Xi1? So Xi1 will be Yn, okay? And then Xi2, so this one will be A21, yeah? So A21, row 2, column 1. So Xi2 will be, so according to this formula, will be Yn plus A21, which is just 1/2 F at the end Xi1, yeah? Yeah, you read off the coefficient from here, yeah? From this, compare with this formula. And then you have Yn plus 1 will be equal, so you have, so you stop at Xi2, right? Because there's only 2 rows, yeah? The number of stages is the number of rows in the table. So Yn plus 1 is just Yn plus, you know, I mean, you have to use this formula, so, and now I have Yn plus H, then, no, yeah, so I have to use this formula, yeah. So then I have to use B1, so what is B1? So B1 is 0, so nothing here. So I got B2 only, so B2 is just 1. So then I have 1, so F at the end plus, so C1, so C1 will be 1/2, no. So B1 equals 0, so nothing, yeah? Should be C2, yeah? So C2 should be 1/2. So H over 2 and Xi2. Okay, so that is this method. So this method. With respect to this table. And maybe we do another one. So maybe suppose we do this one. So suppose I have 0 here, 2/3 here, 2/3 here, 1/4, 3/4. So again, this one is my C1, this one is my C2, this one is my B1, this one my B2, and this one is A21, yeah? And I just have Xi1 equal Yn, and Xi2 will be equal Yn plus 2/3 H F Dn Xi1, yeah? Remember the general formula? General formula is here, okay? And then after that, you just have Yn plus 1 equal Yn plus, okay, so now I have B1 is non-zero, so I have to be careful, okay? So I have H over 4, yeah, for the first B1 here, then F Dn plus C1, so C1 is 0, so I have Dn Xi1, yeah, plus 3H over 4, because this term, yeah, F at Dn plus C2H, so 2H over 3, okay, and then Xi2. Okay, so that's, you see, the different table gives you a different implementation. And once you have those formulas, you can implement it easily, right? I mean, and you can do the last one. So this one is exercise, but you can do the last one. Maybe let me do it. So Xi1 equal Yn, Xi2 equal Yn plus, so A2 is just H, yeah? So F Dn Xi1 and then Yn plus 1 is just equal Yn plus H over 2 F Dn psi 1 plus h over 2, yeah, because h over 2 come from here. So f Tn plus h psi 2. Okay, so you get the idea, right? So how we read off? So this one is just B1, this one B2, and this one is C1, this one C2, this one is A21. So different coefficient give you a different formula for yn plus 1. Okay? So the matrix A is called the Ronskotter matrix, archive matrix. And you know, this vector B called weight, and this one nodes, just a name, you know. But the most important thing is from this table, how do you write a formula? Yeah, so the third order Ronskotter method is, you know, I mean, by analyze the Taylor expansion, you know, you have to solve those equations, and you see that there's four equations, but there's how many unknowns? So your B1, B2, B3, and C2 to C3, so 6 unknowns, yeah. So 3 here, so C2, C3, 5, and 8, 3, 2. So 6 unknowns, and you have only 4 equations. So you have a number of order 3, yeah. So look at this one. So this one is 2 possibility for Ronskotter method order 3. Okay, and we can write out the formula as well. So suppose I have a table like this. So this one is 0, 1/2, 1, and this one is 1/6, 2/3, 1/6. So 1/2 minus 1 and 2. So, you know, I mean, you have to start with the general case, but this one, you know that there should be psi 1, psi 2, and psi 3. Yeah? Because according to the general formula, you know, the number of psi equal the number of rows in the table. So we have 3 tables. So we should have psi 1 equal yn here, and this one psi 2 equal yn plus. So this one will be your A21, yeah, and this one is your A31, and this one is your A32, yeah. So now psi 2 will be yn plus h A21, so will be h over 2 then f of Tn psi 1, yeah. And now psi 3 will be yn plus. So now have to be careful a bit, yeah. So now you have A31, yeah. So you should have minus h f Tn psi 1, okay. And now the second term will be 2h, okay, because you have 2 here, yeah. So you have 2h f of, so here you have Tn C2. Okay, so now this one is your C1, C2, and C3. So it should be Tn plus h over 2 psi 3. Okay. Oh, sorry. One should be psi 2, not psi 3. And then you have yn plus 1, it's just yn plus h over 6, f Tn psi 1, so 1/6 come here, then 2h over 3, ftn plus h over 2 xi 2 plus h over 6 tn plus, so c3 is h xi 3. Okay, so given a table, you can write down the formula for yn plus 1 easily. Okay, and if you don't write the correct formula, your ODE solver is not going to give you the good numerical solution. Okay, so this is the fourth order Ronch-Cotton method. Just write out the formula, and you can implement this in MATLAB. And so this one is the fourth order Ronch-Cotton method, and it used very, very widely. Okay, so that's why I want you to implement this at least for once in your life. You should know.